Welcome to Lecture Online, and now we're going to do another series on simple harmonic motion, but this time we're going to do it with damping. There's going to be a damping factor in there. Of course, where we should start is with the simple case where there's no damping yet. We're just going to go through the fundamentals of simple harmonic motion, trying to develop the differential equation, and then we'll find the different solutions of the differential equation with the damping factor involved. So let's start with the simple case right here. We have a simple string hanging from a ceiling, and it's currently unstretched because there's nothing hanging from the string, and we're assuming that the mass of the spring itself is 0, so it does not sag under its own weight. So then we add a weight to it. We allow the string to stretch some distance. The distance here is s sub 0, and now we have this in equilibrium, meaning there's no motion there. It's simply hanging from the string. The string is being stretched at distance s sub naught, and x equals 0 is the equilibrium point for its eventual motion, because once we put the string in motion, the object in motion, it's going to oscillate back and forth about this point right here. So it's s sub naught below the position where the spring would be if there was no mass attached. So in the case of static equilibrium, we can use Newton's second law to say that in case number 1, that F equals ma, and of course in this case F, and we could say F net, of course, equals ma. In this case, F net is going to be equal to 0 because there's no acceleration, there's no motion whatsoever. So what are the two forces? Well, we have the force of the spring pulling back upward. That's F sub s in case 1. And we're going to call that equals to minus ks sub 0. Now, the minus always confuses a lot of students. And why does it do so? Well, you see the force pulling upward, and yet they have a negative there. But what you have to keep in mind, that downward is considered negative, upward is considered positive. So from this position to this position, there's a negative s sub 0 displacement. So s sub 0 is a negative quantity, so the negative times this negative makes it a positive, so it is actually correct. So we have to keep that in mind. On the downward force, this is caused by the force of gravity. Of course, the force of gravity is equal to m times g. Now, again, there's a source of confusion here. We have to be careful. G sometimes is written as a minus 9.8 meters per second square, especially with equations of kinematics, because negative, of course, downward is negative, and G is, of course, a negative acceleration. But if we simply call it a constant, G is simply 9.8 meters per second square, then the force downward caused by gravity has to be written as a minus mg. So in this case, G is indeed a positive quantity. So now when we find the net force, we have to add those two together. So we can say that F s sub 1 plus F due to gravity is equal to 0. And then if we place the quantities in there, we can then say that minus k s sub naught minus mg is equal to 0. And then we can move one of them to the other side. We can then say that minus ks0 is equal to mg, or we can say that ks0 equals minus mg. Minus mg. There we go. All right, so that's the static situation. Now what happens when we pull on the mass and we let go and it starts oscillating back and forth, and we catch a snapshot of it being in this particular situation, a distance x below the equilibrium point. This is now considered the equilibrium point of the simple harmonic motion. And so even though it's below, it could be that the object is in the process of moving downward, it could be that the object is in the process of moving upward, or it could be that it's stationary because it's reached its maximum amplitude. We don't know. We don't really care at this point. We just want to look at the general equation. So what we're going to write here in case number 2, we're going to write that F net equals mass times acceleration. In this case, there will be an acceleration because it is constantly changing speed, and therefore, yes, there will be an acceleration depending upon what the sum of the forces are at that moment in time. So again, what we can say is it's going to be the sum of these two. So F2s plus F due to gravity, and I guess I should put a little g underneath here, F due to gravity is equal to m times a. Now if we plug, when we put in there what those are equal to, we can say that F2s is equal to minus ks sub naught minus kx plus a minus, well actually I'll just might as well make that a minus, minus mg equals ma. Now to simplify that, I can come back over here and realize that ks sub naught is equal to minus mg. So I can go ahead and plug that in there. So this becomes minus a minus mg minus kx minus mg equals ma. And again, just to make sure we have the signs correct, notice that when x is negative, this is a negative x and this becomes a positive quantity. So again, keep that in mind. So minus times a minus becomes a plus, so we have mg minus kx minus mg equals ma. And notice that the mg's cancel out, and so we're left with minus kx equals ma. And let's see, I can write all that on one side. I can simplify this as saying 0 is equal to ma plus kx. Then what I could do is divide both sides by m, and there's a reason why I do that. You'll see that later. 0 is equal to a plus k over mx, and then I could take advantage of the concept that the acceleration is equal to the second derivative with respect to time of position, which can also be written as x double dot. So x with two dots on top simply means the second derivative of that variable with respect to time. This only works when we take the derivative with respect to time, so there's a special notation for that. If I employ that, I can then say that 0 is equal to x double dot plus k over mx, which now becomes what we call the differential equation, the equation that describes simple harmonic motion like that. So this may be a slightly different way of looking at simple harmonic motion. I have some other videos that actually looks at this slightly differently, coming up with some what we call a different set of equations, but ultimately those equations were derived in part by this general form of that differential equation. Now what we're going to do in the next video is we're going to solve that equation, that general equation for simple harmonic motion, come up with something that you'll recognize if you've seen simple harmonic motion before, and then we're going to add the concept of a damping factor in there. We'll solve the same equation with a damping factor, see how that changes the equation, find the general solution, and then look at the various cases with overdamping, critical damping, and underdamping taken into account. So this is your basic concept of simple harmonic motion. Hopefully that rings a few bells for you. You say, okay, I see that, I recognize that, I understand that, and then you'll see how we actually solve that in the future videos.